So this is lecture 25 and 26. What we did in the last class. Let's have a quick recap of that. I showed you the mathematical definitions of the various components of the inertia tensor at point A relative to a given Cartesian coordinate system. That Cartesian coordinate system had its origin at that point A, which is appearing here. I also tried to share with you my understanding of the physical meanings of those 9 components of I, A, I, J, those 9 components. 3 of them are called moments of inertia, the diagonal elements of that matrix, and the off-diagonal elements are called the products of inertia. To the best of my ability, to the best of my knowledge, I tried to explain that to you. Then what did we do? Then I showed you what is called the perpendicular axis theorem for the inertia tensor. I showed you the proof as well, and then I showed you the parallel axis theorem. That also I proved in the last class. Okay, so these are the topics we covered. Now moving on, next we want to study what we call as the principal axis of the inertia tensor of an RB at point A. Principal axis. What is meant by principal axis? I will define. So let's consider this body M, RBM. A is a point which is fixed on the RB as usual. And I have shown 3 axes of a Cartesian coordinate system which has its origin fixed at A. Okay. Given this context, given this diagram, this axis x1 e1 is an axis, right? Is an axis. E1 is a direction. E1 gives me a direction. X1 e1 gives me an axis, and that axis is passing through A. And this axis will be called a principal axis. I will use the acronym P axis of the RB at point A, or rather of the inertia tensor of the RB at point A if these two conditions are satisfied, then we will call x1 e1 as a principal axis of inertia of RB at A. Extending the same definition and in the context shown on the screen, x2 e2 is called a principal axis. Under certain conditions, x2 e2 can also be a p axis. x2 e2 will be a p axis of the inertia tensor, same words what I used last time, I mean here, same words here, at a if I do want to remind you that inertia matrix is always a symmetric matrix, right? So please keep in mind that IA13 is always, maybe I write it here, remember, maybe it's too small here, I'll write it here. Always a 3 by 3 symmetric matrix. It's always symmetric, which implies that you can use IA12 and IA21 interchangeably. They are always the same. Similarly, IA31 is always equal to IA13 and IA23 is always equal to IA32. Okay, do keep this in mind. Do keep this in the background while I make statements about the p-axis. Why am I reminding ourselves of this? Is because I could have as well written this condition as IA320 and IA210. Makes no difference. So these two are same. IA23 being 0 is same as IA32 being 0. IA12 being 0 is same as IA21 being 0. What is important, if X2E2 is a principal axis, when those components, those off-diagonal components of the inertia matrix which involve 2 as an index are 0. So see, 2 is here, and for X2E2 to be principal axis, all the off-diagonal components of the inertia matrix that have one index as 2, those have to be 0. Then only X2E2 will be called a principal axis. Same thing was happening here. X1E1 is a principal axis when the inertia component, off diagonal inertia component involving 1, 0. IA130, IA120. This is how it is defined. Okay. Alright. Similarly, I can say that X3E3 is a p-axis of the inertia, same words, at a if, what would be the condition? I've already told you how this index is related to the condition of this axis being a p-axis. So since I have 3 here, thus the two conditions that must be fulfilled for X3E3 to be a principal axis are IA310 and IA320. Okay, this is how we define principal axis. Now realize the fact that x1 e1, x2 e2 and x3 e3 are all mutually perpendicular axes, right? Because they are axes of a Cartesian coordinate system. So these three are always perpendicular to each other. Right? Also realize that if you know x1 e1, I have written here, if x1 e1 and x2 e2 are already known to be the principal axis of the inertia tensor of RB at A, it automatically follows that x3 e3 must also be a principal axis. So if you have found two perpendicular axes to be the p axis of the RB at point A, the third perpendicular axis will automatically become a p axis. I can show you quickly. So if we know x1 e1 is a p axis, it means what? It means by definition IA12 is 0 and IA13 is 0, right? A pair of conditions. And if we already know x2 e2 is also a p axis, what does it mean? It means IA230 and IA210. So I have four conditions. I know four components to be 0 of the inertia matrix. 1 2, 1 3, 2 3 and 2 1. Now focus on these two. IA130 and IA230. Both components have 3 as one of the indices and both are already known to be 0. Right? Since IA130 and IA230 known, it automatically implies that x3 e3 must be a p axis. Alright, so knowing two principal axes at a point is enough to know the third p axis also. On its own, you get that for free if you are aware of the first two p axis. The third p axis is automatically known. Keep this in mind. Now let's ask this question that if I know the inertia tensor at a point, is it guaranteed that a set of three mutually perpendicular axes exist or not? Existence of a set of three mutually perpendicular p axes. So this is a statement I am making. Since inertia matrix of the RB at point A is a symmetric matrix with real values, right? All components will be real. By real I mean they are not complex. They are not complex numbers but are real numbers. It is guaranteed that at point A the inertia tensor of RB will always have a set of three mutually perpendicular axes. Always have at least one set of three mutually perpendicular p axes. It may have even more, but at least one set of three mutually perpendicular p axes it will always have. Why is it important? Why are we worrying about these principal axes? Now recall that the angular momentum of an RB is expressed in terms of the inertia matrix and the angular velocity of the body. Right? This is the equation we wrote. Now if you use the information that is ingrained in this matrix equation and you write the angular momentum of the body, it will be written as right, and then on the right hand side you will have right plus more terms, some terms along E2 and some terms along E3. Okay, written the fully expanded form. In this form, what is happening is that H1, the component of angular momentum along the E1 direction, is dependent on all this bunch of terms. So you have H1 depending on omega 1 as well as omega 2 as well as omega 3. Same thing will happen with H2. H2 is also depending on omega 1, omega 2 and omega 3, and H3 is also doing the same. So there is a cross coupling. There is a cross coupling between the components of angular velocity and the components of angular momentum. Again, during JEE preparation and school days, you never came across this situation. I am very confident. In those days, H1 was only dependent on omega 1. H2 was only dependent on omega 2. H3 was only dependent on omega 3. Here it's not the case. In the most general scenario, this is not the case. There is cross coupling. HF components and omega MF components in general. Now you consider the scenario that somehow I am able to find a set of three mutually perpendicular p-axes of inertia at point A, and I use those three axes to be the axis of my Cartesian coordinate system. So my working coordinate system has, I go to point A, I set a working coordinate system, Cartesian coordinate system, like this, right? And corresponding to that, I have this cross coupling. So far, general cross coupling is existing. But now, if I tell you that if x1 E1, x2 E2, and x3 E3 form a set of mutually perpendicular, that's not even required, a set of p-axis of IA at point A, and that is not required, I have written IA. Then what happens if, since x1 E1 is a principal axis, this implies that IA12 0 and IA13 0. Since x2 E2 is a principal axis, it implies that IA230 and IA210, right? Go back to this coupled form of equation. Now if I focus on H1, what is happening? This will vanish, this will vanish, this will vanish. And now you have a situation when H1 is simply IA11 omega 1. You go back to your good old days, school days, when there was no cross coupling and H1 was entirely dependent on omega 1. That is still possible if you choose 3 p-axes to be the axis of your working coordinate system. Same thing will happen here. You see, if you talk about H2, right now it is I21 omega 1, I22 omega 2, I23 omega 3. But if 2 is a principal axis, what happens? This goes away, this goes away. IA22 omega 2, that's all. And similarly, H3 will be IA33, that's all. So this, I am summarizing, H11 will be IA11, H2 will be IA22 omega 2, and H3 equals IA33 omega 3. Cross coupling disappeared. Great advantage. That is why we worry about principal axis. Okay. So going back to this existence issue, I am telling you that inertia matrix has always 3 mutually perpendicular p-axes hidden at every point. And since we have seen the advantage of knowing these p-axes, The next curiosity that we raise is, how do we identify those p-axis of inertia at a point? Right? So it has great advantage, and we also know it always exists. So the next question is how to find p-axis at a point A. There are two ways. There are two ways to find. The first one is what we call as the eigenvalue analysis. In one of your maths courses in the first year, you might have been exposed to this idea of doing what is called the eigenvalue analysis of a given matrix. In your maths course, it must have been presented for a given matrix. In this course, that matrix is the inertia matrix. So whatever you have learned in your maths course can be applied here. You can do the so-called eigenvalue analysis, and that will give you eigen directions. That gives us eigen directions, three eigen directions, three of them. And guess what? Those three eigen directions are nothing but the p-axis of IA. Those three directions will be p-axis. Will always work. Will work for all RBs at all points. So this is the first way. The second way is to identify symmetry planes in your RB by visual inspection. Visual inspection. Identifying a plane of symmetry passing through a plane of symmetry of what? Plane of symmetry of the plane of symmetry of the body. Of the RB at point A. Or symmetry of the body RB passing through point A. Passing through point A. Now the second method will work only when such a symmetry is recognizable. Only if it is obvious but that you can identify such a symmetry by visual inspection, then only it will work. Works only for some bodies, some RBs at some points. May not work all the time. Okay. Whereas the left hand side, on the left hand side, what I said, the eigenvalue analysis will work for all RBs at all points. The second one is good if the plane of symmetry exists, and in that case you don't have to do detailed eigenvalue analysis. In this course, only this one will be considered. I am not going to ask you to do any eigenvalue analysis in this course. We will rely only on visual inspection, which means that the bodies that we will consider will have some symmetry, and then only you can use the second one. Since I am not going to ask you anything about eigenvalue analysis, I am not going into any further details of method 1. And since I am going to ask you to identify some p-axis using method 2, I need to tell you how exactly you use visual inspection, how exactly the method 2 works. I will explain it. Okay. That's strange. Now I had some pictures saved on slides. I'm not able to see them. Let me see where they are. Hmm. Yeah. How to identify a p-axis when the body has a plane of symmetry? Let's consider this. Let's consider this diagram. This is a picture of an aircraft. Now I have shown a plane on this figure. I have shown a plane. I have tried to show a plane. Okay. What is this plane? This plane is the mid plane of the aircraft, going from the nose all the way to the tail. It divides the plane into two halves axially. This is a symmetric plane. This is a plane of symmetry. Now it is a plane of symmetry either when the aircraft is completely vacant, nobody is inside, or when all the seats are occupied and we are assuming more or less every passenger has the same weight. So that is the approximation I am making. Maybe it is easier to work with the case when there is nobody sitting inside the aircraft, and then indeed this plane will be quite accurately a plane of symmetry, right? My claim is that if I can identify a plane of symmetry like this, then, and that plane of symmetry I call as shown here, if x2e2, x3e3 is a plane of symmetry of the RB and it passes through A, passes through point A. I hope you can see where I have marked A. A is here. This is the point A. Okay. If x2, e2, x3, e3 is a plane of symmetry of the RB and it passes through point A, then my claim is x1 e1 axis, which is not clearly visible here, but this is the x1 e1 axis. This red axis that I am trying to draw, that is the x1 e1 axis. The next one even axis is a p axis. That is the statement I am making. This is true. My statement is true. But why is it true? How can we prove it, or how can we convince ourselves that what I am saying is right? Consider a mass dm here. Consider a mass dm here. Okay. And its coordinates are x1, x1, x2, x3. Refer to which coordinate system? Refer to the coordinate system that I am showing. x1, e1, x2, e2, x3, e3 with A as the origin. For every dm with coordinates x1, x2, x3, it is guaranteed that you can find another dm which will have coordinates minus x1, minus x1, x2, x3. It is guaranteed. Why? Because I have shown you the plane of symmetry. There has to be a point, has to be a small chunk of mass with minus x1, x2 and x3 as coordinates. What does it mean as far as the inertia components are concerned? Recall, IA12 is what? IA12 is minus x1, x2 dm. What is IA13? IA13 is minus x1, x3 dm. So what will happen is that this dm, I am focusing only on the two shown chunks of mass on my figure, they will have some contribution to IA12 after all. So dm on this side will come with contributions like dm times x1, x2. But that contribution will be counterbalanced by the dm on the other side, which will come with the same mass minus x1, same x2. Right? And these two will cancel. Sorry, not with minus dm but with plus dm, because minus I am leaving here. It will come with plus dm minus x1, x2. These two will cancel. And this will happen for every dm that you choose on this side. There is a counterbalancing dm on the other side. That's what the plane of symmetry means. And eventually this will become 0. Now let's look at IA13. The same dm will contribute what to IA13? It will contribute dm times x1, x3 from this side, and then it will contribute dm minus x1, x3 from this side. Same consequence, they cancel out. And again, I am repeating that this will happen with every chunk of mass on this side. There is a counterbalancing mass on the other side, making this IA13 0. Now if you have IA13 0, you have IA12 0. Indeed, by definition, x1 e1 is a principal axis. This is why this visual inspection method will work. So we have identified one p-axis here. Can I identify more p-axis using visual inspection of the inertia at the same point A? That will require more planes of symmetry to be existing and passing through A. For this RB, an aircraft, is there any other plane of symmetry which passes through A? Is there any other plane of symmetry besides X2E2 and X3E3? The answer is no, in my understanding. If you consider the plane X1E1, X2E2, clearly that is not a plane of symmetry. The front part of the aircraft is not symmetric with the rear part of the aircraft, not at all. If you consider the plane X1E1, X3E3, which is sort of horizontal plane, is that a plane of symmetry for the RB? No, it doesn't look like. Definitely because of the engines. Engines are below X1E1, X3E3 plane, and there are no engines on the top. That itself tells me that X1E1, X3E3 is not a plane of symmetry. So for this body, I cannot identify any more p-axis at point A by visual inspection. Okay, so visual inspection helps us find only one p-axis. Does it mean the other two axes do not exist? No, you cannot make that statement. In fact, the other two axes also exist, and they can be found by doing eigenvalue analysis. It is just that visual inspection method is not helping me identify that. I will write it here. Also exist, hidden, can be found by eigenvalue analysis. VI won't work. VI means visual inspection. VI, I mean visual inspection. Okay. I hope it is clear to you. Now I want to share with you a word of caution. If you can find a plane of symmetry implies existence of a p-axis which is perpendicular to the plane of symmetry. Always. And the arguments that I gave on the previous slide, they will hold good always, and that's why I am confident that a plane of symmetry will always give me existence of a p-axis. However, keep in mind that if somehow you know a p-axis, do not jump to the conclusion that the plane which is perpendicular to the known p-axis is always symmetric. Do not jump to this conclusion. If you know a p-axis, the plane perpendicular to that p-axis may or may not be a symmetry plane. It doesn't work like that. But it works the other way always. If a plane of symmetry is known, then the axis perpendicular to the plane of symmetry will always be a p-axis. Do keep this in mind. Okay. I'll take a couple of minutes and then we will have a break. Earlier I have already shown you that if I know all three p-axes, mutually perpendicular p-axes, and if I name them as x1, e1, x2, e2, x3, e3, what happened to the inertia matrix? It reduces to this form. Right? It reduces to this form. When all three are principal axes. Right? Diagonal matrix, it reduces into a diagonal matrix, which is the ultimate convenience as far as algebra is concerned, and we would like to have this as much as possible. I would like to work with a coordinate system which has axis as the principal axis, because it reduces the matrix into a diagonal matrix. Sometimes you are not able to find all the three principal axes, but if you know, for example, last example, aircraft, you don't know about the other two axes, but you still know x1, e1 is a principal axis, and you still have to solve a dynamics problem. At least use that much information. So in that case, for the aircraft problem, what will happen? What will be the simplified form? In general, you will have the three diagonal components, but this IA12 will be 0, and since IA12 is 0, IA21 will also become 0. So I am talking about when at least x1, e1 is a p-axis. That case I am trying to simplify here. So x1, e1 is the principal axis, IA12 and IA21 are 0, IA13 and IA31 will also be 0. Right? Anything else we can set as 0? No. If you don't know any more p-axis, without any further information, you should retain, you will still have these as non-zero. Is it better than the fully populated matrix? Indeed it is. Out of 6, at least 2 you have removed. Or out of 9 places, 4 are 0. You have to deal only with 5 non-zero values. Still a good idea. As your working coordinate system, I am talking about the aircraft example. As an aerospace engineer, I would like to work with this coordinate system. And this is definitely the best case scenario. The best scenario for any analysis. Because only 3 diagonal components are non-zero, rest are on zero. Alright, let's take a break. We come back and meet at 5 past 5.